Hello students. So I'll be talking about balancing of masses in this lecture. So we have already explained how to balance state yes a single mass, okay, or several masses which are in the same plane. Okay, one single mass can be balanced by another mass in the same plane. Okay, and now today we will look at the balancing of single mass by two different masses rotating in different plane. uh, by the way, this is a single mass, okay, which is away from at a distance of r. Mass is m, which is away from the axis of the rotating shaft, okay, at a distance of r. So this mass will cause some unbalance in the shaft, right? So here, uh, yeah. So we will have we what we can do is we can have two masses, one here, okay, at a distance, radial distance of r1 for this mass m1 and r2 for this mass m2, okay, from the axis of the shaft, and also an axial distance. So this is the location of first mass that was unbalanced previously. We place these mass m1 and m2. These two masses are away from the plane of the plane of this mass, okay, which are the first mass is away at a distance of L1. Okay, let me use the marker. Okay, it is this at a distance of L1 from this one. Okay, I mean this is the location for the first one, this is the location for the second one. So their gap, axial gap is L1. Similarly, this is the location for the third, or sorry, the second balancing mass from the initial mass that is unbalanced. So the distance from this one to this one, the distance between their plane is L2. Okay, all right. Now we can actually draw it from we can draw the side view of this by looking from this side, okay, from this side. So if you look from this side, we have this type of diagram, okay. So you can see this one m is here and other two masses are here. I mean these two are at same plane, m1 m2. So let's assume that r1 is more than r2. So r1 is here, which is more than r2. Okay, we just place it like this. All right, now see, you just have you can read this. L1 is the distance between the planes of this mass. M is the capital M is one plane for this small mass m. Capital N is a plane for this m2 mass, and capital L is a plane for this m1 mass. So L1, L2 are distances between them, and L is the distance between the planes L and N. So actually total length has been assumed as, okay, L, right? All right, now how to balance it? This is centrifugal masses by this centrifugal force by mass m. This one will be what? M r omega square. Distance is r. For this one, this will be m1 r1 omega square. All will have same omega, so that's why omega square we will not write as omega 1 omega 2. We will write omega only because it is same for all the masses. So this one will have m r omega square, this one will have m1 r1 omega square, and this one will have m2 r2 omega square. Okay, all right. Now, sorry, okay, next we have centrifugal forces by these two forces we have written. Now you know that unbalance is caused by this one, this mass m. Okay, that is unbalanced centrifugal force will be balanced by centrifugal forces caused by these two. Okay, so we can have the unbalance caused by the unbalanced mass will be balanced by the addition of these two centrifugal forces. So we call it a static balancing. Okay, this part static balancing. So where we can just write m r omega square will be equal to m1 r1 omega square, m2 r2 omega square. Omega square gets cancelled out because it is same, and we have this as the condition for static balancing. Okay, now we have actually, since the masses are at different planes, okay, we will have their moments also. So now you see, you can see this one here, you see this one, this is a force, okay, this is a force, and this is a force. These three forces are shown. Now you see, moments about any point caused by the masses should cancel. So the thing is, all the moments, now see, suppose about this point, suppose, about this point, this force is causing a moment. Yes, this force will cause a moment in this direction. Yes, this force will not cause a moment because this is passing through the point itself. So if this one and this one, these two are equal, then only it will be balanced, otherwise it will swing. Okay, whirling will take place. So that also should be balanced, the moments. Okay, so the moments has to be balanced, means we have to take a point, okay, about which the moments, all the moments, we have to find the moment. How will we find the moment? If we take point A, then moment of FC will be FC into L1. Okay, force into perpendicular distance. Similarly, about point A, moment of this FC2 will be FC2 into L. Okay, and if I take another point, let's say if I take point B, then we will have a moment of FC and FC1. FC will be FC into L2 because FC is the force here and L2 is the distance from the point B. Similarly, FC1 is going downward and the distance between point B and this force is L. Okay, so we have to equate their moments. This is called dynamic balancing. Right, let's see how to do. So we have taken moment about B, okay, and summed it up to which is equal to 0. So we have to make it 0 before dynamic balancing. All the moments should cancel each other, so that will make it 0. So here we have written, as I have said, like moments in left hand direction, unlike moment in right hand direction, right hand side. So we have written this, replace FC1 value, FC value. So we can find out M1R1 from here, which is equal to MRL2 by L. So we need to actually have one of them, okay, either M1 or R1. Okay, in the question it will be given that which one, I mean, we may not know the mass, but we will know the radial distance. Similarly, if mass is known, radial distance will be asked. Okay, similarly, say we can find out M1 R1 from here. Okay, and similarly M2 R2 can be found if we take the moment about A. So about A, if we take, can find out M2 R2 equal to MR L1 by L. Okay, these are called dynamic balancing conditions. Okay, so we will use them in later numericals. Let's see the use of this one. We will see that thing in the coming numericals. Now let's understand one more thing, that this actually I have already explained. Okay, so if all the masses are in the same plane, several masses, more than one masses are there, then how to balance? Okay, if they're in same plane, then dynamic balancing question will not come, because they're in the same plane and this length L1 L everything will be 0. So there is no question of dynamic balancing when they are not, when they are at same plane. But when they are not at same plane, they are different plane. This one is having one plane, this one is having one plane, this one is having one different plane. All these are at different planes. You understand? Different plane means this will have, see, we just take a plane like this. Okay, passing through this will place this mass at this plane. Obviously this is, this second and third ones, they are not at this plane, they are away from this plane. It is in this direction, the other one is at that direction. There is some gap between them, so they are not in the same plane. So if they are not in the same plane, we'll have dynamic balancing, otherwise we'll have only static balancing. So we have seen that this static balancing, how to do it. Okay, and this was already explained in class, so I'll not go through this one. Balancing of several masses in the same plane. Let's see how, what happens. Okay, if we have this balancing of several masses in different planes. Okay, this will understand now. Balancing of several masses in different planes. Okay, so now we have seen just single mass balancing, no, just now this one, single mass balancing with masses of different plane. Now balancing of different, more than one mass, okay, in different plane. What to do in that case? What you can do is, here you see, one condition to learn before that is transference of a force from one plane to another. What we can do is, we can take this, see, simply we have a axis, your that shaft, and we have a mass at a radius r. Okay, what we can do is, this will know that this mass causes a what, centrifugal forces m r omega square. Omega square is not written by the way because this will cancel out. So m r omega square is the centrifugal force. Fc means force centrifugal. Okay, centrifugal force. So this one is going on. We want to take this force here. Okay, but how to do it? We can take this force at a distance of L. Okay, this is the original one, and this is the transference of to another plane. This was another. This was the original plane. We have taken this force to this point. Okay, for that, what we have to do is see if once we take this force here about this original plane, this will cause a moment. Okay, moment, and this has to be cancelled by an equal and opposite moment. Okay, so such in that case only there will be no change. Otherwise, if you have taken a force here, this will cause, see, this will cause a couple. Okay, this will cause some rotation in this case. So we have to take an equal and opposite moment in this case. Now see, since we have taken an equal and opposite moment force here, okay, let's say this is equal to that mr omega square only. Okay, so we have not written mr omega square here, we have written this mr. So this force and this force will cause a couple. Okay, see, this is the couple, and the couple will be acting about this oa line, perpendicular line, which is perpendicular to the axis of the shaft. Okay, so now we will have two actually couple vectors. One will be actually from the centrifugal force, okay, mr, and another one because of the distance, that moment, okay, about the plane. This one mr, this force will cause a moment about this point. See, this is the force is mr, length is l, so mrl will be the, okay, will be the value of the couple. We can take it as couple, force multiplied by the distance. Okay, that is the couple only, right? So this is the couple value and this is the force value. Okay, now what we can do is we will use it later on. You just read whatever is written here. Okay, so how to do it? Actually, we have to take a couple at this point. Okay, so here you see I'm going a little bit quickly because you can read and understand this thing. So let's explain this part. For balancing problems, the couple vectors are drawn by turning them through 90 degree so that they are parallel to the force factors. This does not affect the relative positions. Okay, now what to do? Let's explain here also, here only. Let m be the mass. Okay, it is there at this. It's to be transferred to a length l. So in this plane, second plane, where the mass is transferred, there should be an opposite centrifugal force Fc2. This is what I told, Fc2, to nullify this effect. Okay, so since originally mr is the centrifugal force at first plane, and there is now an opposite force mr only, equal and opposite mr only, so there they will form a couple. This is what is written. The moment of the couple tends to rotate the shaft about point O. So finally, at the end, to explain it, to summarize this thing, what to do is to transfer a force, existing force, at a distance of L, we need to consider the couple, which will be MRL. That's it, MRL. This is the thing. Okay. So force was MR, take it to a distance L, you multiply L with that. Simple thing. Okay. That is how we transfer the force. Right. Okay. Next, let's see how to balance several masses acting in different planes. Now, let's take this as a shaft. We have to support the shaft at two bearings, bearing 1, bearing 2. Let's write the bearing 1 as C1 and this as C2. Okay, two different bearings. Okay, now we have mass M1 at a distance of R1. We have mass M2 at a distance of R2. And we have another mass M3 at a distance of R3. Now, one thing I told you, when the masses are at different planes or in the same plane also, we need to take a horizontal reference point. Now see, this line is horizontal line. About this horizontal line, the mass M1 is at that angle of theta 1. This m2 is will not measure it in the opposite backward direction. We'll always have to measure in the positive direction. If you have measured this in this direction, theta 1, we have to measure in the same direction. Let's say this is anticlockwise direction. Let's measure it in the anticlockwise direction only, m2. That will be theta 2. Okay. Similarly, for m3, this is theta 3. Understood? This we have measured it with respect to the horizontal line. So now one more thing. Here you see, we have to measure the lengths from of each mass from one reference plane. In this case, we call this as the reference plane of the bearing. Okay, because we have to measure the distances from some point, isn't it? I mean, the relative gaps also may be known, but we have to take moment about a fixed point. So in this case, the general practice is either you take this bearing as the reference or this bearing as the reference and take moment about one of them. Okay, now we will see that this is C1. Okay, so here see, this is the point. We have drawn the free body diagram. So here we have three initial original masses. This is first mass. Okay, second mass is there, m1, m2, m3. Okay, see, m1 is there, so this is m1. Okay, this is m3, this is m2. Okay, right. So now m1, m2, m3, these are known. So we have to place some balanced mass. Now we have to place two balanced mass, mc1 and mc2. Okay, because of the couple caused by all of them, we have to place two masses. You have seen this, right? Before this, we have seen one mass can be balanced by placing two masses. Okay, both sides. So if we have more than one mass here, 1, 2, 3, 4, we'll still balance it in the same manner. They may not be in the same 90 degrees to each other. They may not be parallel to each other. Okay, but all the masses that are balanced has to be placed in either side of the unbalanced masses. So here you see we have placed two balanced masses here and here. Okay, three unbalanced masses are there in between them. So we have just assumed that the angle will be theta c1 and theta c2. Okay, c1, c2 are just horizontal lines here. Okay, don't get confused with this bearing c1, c2. Okay, forget about this c1, c2 here. It is actually mistakenly written. C1 and c2 are the horizontal lines with respect to which we measure their angles, theta c1, theta c2. We call it. Okay, so what are the unknowns here? In this case, m1, r1, m2, r2 all are known. The lengths from one bearing, l1 is the length of the axial length of the m1 mass, okay, from bearing 1. Similarly for m2, axial distance from bearing 1 to the plane of the m2 mass. Similarly, this is the length l3, okay, and the total length between the bearings is lc2. Okay, here. So all right, now we have placed these two balanced masses and we need to know what is the radius, okay, and the mass. Similarly, the mass here mc2 and the radius and angle also. Okay, all three things if we know, one more thing is required, where to place them. Okay, axial distances. So in this case, since if we take this as our reference, then we need to know this length also, okay, from the fixed point to this one and this one also. Okay, so what we do, we have to minimize the unknowns. So we take the reference here and from here we measure all the lengths so that we can take a moment about this one and one of the length is minimized. Okay, one of the length is not required to be found. So with respect to this only we find out the other lengths. Okay, so what to do? Here you see, first thing is we need to balance all the masses. So first thing is the static balancing. So you see, resultant of these three masses has to be 0. So resultant force, see, this is the centrifugal force, centrifugal force, centrifugal force for all of them. So they must be equal to 0. So how to make it 0? By placing in place of 0, we'll write mr. Okay. So now the thing is, this mr omega square, So since we have two masses, so this will be mc1 rc1, okay, omega square mc2 rc2 omega square, okay. Then they have to be equal, which we can write it as all the unbalanced part. This is unbalanced, okay, un I'm writing unbalanced, unb unbalanced, and this part is balanced, okay. This is b balanced. So unbalanced and balanced masses should cancel each other and make this as zero. So what you can write is the summation of all balanced, sorry, this is unbalanced masses plus summation of all balanced masses, sorry, not masses, forces. These are forces. Omega square gets cancelled out from here. Summation of all unbalanced forces plus summation of all balanced forces will be equal to zero. This is called the static condition, static balancing condition. Similarly, we take couple, okay, from about a point, reference plane, okay. So this is m r1 omega l1 omega square. So now you see we take this as the reference plane. So about this, okay, so the force is c, this is the force, right? So what is the force here? m1 r1, okay, isn't it? This one is m1 r1, okay. Omega square is there, but we can cancel omega square. We can write also omega square, but at the end it will cancel out. So m1 r1 force is in this. What is the perpendicular distance between this point l1? Okay, so m1 r1 l1 omega square. See, m1 r1 l1 omega square. Similarly, the next one, okay, this is in this direction. Okay, we take it as m1 m2 r2 l2 omega square, okay, that way. You see, I have not taken sign convention here. You can ask me that thing, okay. This is going in this direction, this is going in this direction, that way you can, we have taken. But see, we'll take them as positive, okay. We'll have to take them, all of them, as positive. If one of them becomes negative, okay, then we'll have to change their directions in this case, okay. That means our assumed direction is wrong. And one the thing is, actually we are making the couple zero, okay, resultant couple zero. So the couple caused by each, so about this bearing, this one is causing a couple, okay. We'll have to take an opposite directional force here. This one will be causing a couple, we have to take an equal and opposite force to this one here, okay. Just like we have transferred it, no, transferred it. Actually what we did is, actually we have transferred this force to this point, okay. Transfer this force to this point, transfer this force to this point, everything at a single point. How to transfer? I told you, no. So we have the force. To transfer this force to a location at a distance of l, you multiply that force with that distance l, okay, and take it as positive. What is the same thing we have done here? This force m1 r1 omega square multiplied by l. Similarly, the force m2 r2 omega square multiplied by l2, so that we have taken it to this point bearing. So ultimately we have converted the problem to a simpler problem, where we have to take all the forces at the same plane, okay. That is what we have done here. Just a moment. Okay, so you have understood this, all right. So so here you see, we have taken we have to add these three forces now, m r l. These are actually couple, huh? So l1, one more thing, this one, this mc1 force, there is no length. We have taken the reference here itself. So mc1 rc1 omega square 0 multiplied by 0, because we have not transferred this anywhere else, so that is not written, okay. mc1 rc1 lc1 into 0, so that's why that part is not there. But mc2 rc2 lc2 is there. See, this one mc2 is at a distance of lc2, right? Lc2. So this is written here, okay. So we have finally written it as summation of mrl, okay. Because of this, I mean, this is actually the generalized written equation, okay. And this is mc2 rc2 lc2. Finally, what we have to do is, we have to take their components, okay. Just like, actually you see this part, this part will have components. Okay, this part will also have components, because they are these forces. See, this one is here, this one is there, this one is here. Okay, another one will be here. Okay, we have transferred all the forces, no? So what you have to do is simply we have to find their horizontal components and vertical components. Just we have simplified this problem to the previous one, where we have several masses in one plane. The same thing we have to do. So here we have actually found their horizontal components. In this direct, all horizontal components we have taken as cos theta. So whatever angle we have, that angle, cos of that angle. Now this one will have cos theta, this one has cos theta c2. Similarly, horizontal vertical components will have sin theta. So simplified them. What we have done is we have simplified these are actually unknowns. Okay, unbalanced, right? So we have to simplify and solve it, so that ultimately we get the unknown as what? MC1, C2, RC2, these are unknown. LC2 will be known to you. So square root of vertical component plus horizontal component. Okay, both of them squared and added. And the angle will be sine by cos. Then we will have 10, right? So summation of all this MRL sine theta and minus of MRL cos theta. Why minus? Because we have just taken this into us in the right hand side. We have got minus. Here also we have got minus. Minus minus get cancelled out. So we can find out theta C2. And remember theta C1. Okay, we have to find out theta C1. How to find, we'll see. Okay. So here you see we have found MC2, RC2, and theta C2. So we have found one of the balanced force. The other one by solving the previous equation. See this equation. So we have known these two now. No? Only these two are unknown, MC1 and RC1. So we can use that equation and find out these two. By the way, here also we have the components. Okay. Again, this will have components. So what you can do, MC1, RC1, cos theta C1. This we have taken in the left hand side, and we have taken this and this to right hand side. So and writing their components. So mr into cos theta will have these are actually your horizontal components. So this one will multiplied by cos theta c2. See, this one will have this equation is for horizontal component, and this is for vertical component. Okay, and by squaring and adding them, we can find out MC1, RC1. Okay, and we can find an angle tan theta C1 also. Right. So we can use these equations to solve the numerical. So in the next lecture, we'll solve this question, and we'll see how to apply this concept. Okay. So thank you. We'll finish here. Just a moment.